Okay, hello YouTube. I'm back for another tutorial. I think this is the 7th tutorial in my series of Mathematica tutorials. So today I am going to do some problems on arrays. So introducing some more functions on dealing with arrays. Okay, so the first one involves rotating an array to the right and partitioning, etc. And then we have a problem on an array that deals with binary and base 10 representations. And then let's see if we get to this problem, number 18, power mod. So power mod is a built-in function to help you calculate an integer to the power of another integer modulo a number, but to do so efficiently. So it's a lot faster to use power mod than to actually calculate a number to the power of something and then take its remainder. Right? So really, if you were doing this without the built-in functions, you would use repeated squaring to do this question 18. All right, we can do that, but since this is a beginner's video, we'll save that for another session. All right, so I'll get into it, and let's begin with question 16. So comment question 16, and let's have a read. Using only the following built-in functions: table, if, length, partition, rotate right, delete cases. So this is a new one in the repertoire. Prime Q, we've seen this one before. Form a set, well, it's really going to be an array. Form an array of the first 100 squares plus 1. And then remove those elements of S, which are prime numbers. Then partition the resulting array into triples. And finally, rotate the set, which is an array, 5 places to the right. Okay, so let's try this. So where do we want to start? Well, probably with the collection of the first 100 squares plus 1. All right, so to do that, I'll write table. And let's table over j, why not? So j squared plus 1. And j goes from 1 to 100, right? Because we're listing 100 of these numbers. All right, so I press Shift and Enter, and here they are. All right, so let's just double check. 1 squared is 1, plus 1 is 2, so that's fine. 2 squared plus 1, that's 5. Yes, so these look correct. Okay, now let's have a look at the next task in here. So form a set. Okay, we've done that. Well, it's an array. Remove the elements of S which are prime. All right, so at this stage we want to ask a question: is this number a prime number or not? Right now we want to remove the ones that are prime. Okay, so let's go n equals this right here. Okay, and then we want to know, is this prime? Prime Q n. All right, so this will be true or false. So if it is true, we want to throw it away. All right, but what I'll do is put if this is the case, put 0, and otherwise put n. Okay, so let's have a look at what this does. Okay, so what we have now is, well, the same numbers, except the prime numbers are replaced by 0. All right, so 2, 5, and so on. Now, we want to remove the ones that are prime, so it's easy to just remove the zeros from this list. Okay, so I'll use delete cases to do that. Delete cases. Notice that the word cases is uppercase here. and delete is 2. This is one function. There are two words. The beginning of these words are uppercase. Okay, so at the end of this, comma, what do I want to delete? 0. I'm going to delete the zeros out of the list. Okay, so now the zeros are gone once I press Shift Enter. Now, because this is getting a little bit lengthy, I want to pull some of this out. Alright, pull some of it out and call this S. Say S equals the list with the zeros in it. And then I want to take S and get rid of the zeros from it. Now it's a little bit more clear to see what's going on if you were to read it again. Okay, so still we have the same output. Alright, so have we done the task? Not quite. So we've removed the elements that are prime. Now we should partition the set into triples. Well, look, what we want to do is see if we can partition it into triples. So let's call this array T. And then we want to find out how many elements does T have in it. So we'll use the function length of T. And now I'll put a semicolon there so I don't have to see the output of T again. Let's try again. Okay, so there are 81. Now 81 is divisible by 3. Okay, so that means that we can partition. Now partition means break up the array into subarrays. And in this case, we're going to do so so that the subarrays have length 3. Okay, so I will use the function partition. T. I'll put comma 3. Alright, and I'll show you what comes out. Now we have broken this array T up into 3s. You see how there are these brackets around the triples. Okay, that's what we wanted to do here according to the task. Okay, now that we've done that, let's continue reading. Partition it into triples, and finally rotate the array 5 places to the right. Okay, so let's call this the array U, and I'll put a semicolon, and I'll use the function rotate right U, comma 5. Okay, let's see what we get. Now we don't need the length anymore. Shift and Enter. Okay, now we have moved the array over 5 places to the right. Look, let's just have a look at the array U so we can actually see what's happened here. Alright, so this array U begins with the triple 10, 26, 50. Now where has that gone in the new array? 10, 26, 50 is now the 6th element of the new array. Alright, so we have basically taken this and moved this way. Follow my mouse from left to right. Okay, 5 places over. Now what happens to the end? 5, well, they get tipped off the edge and they go back to the beginning. Alright, so that's why the first one in the new array is this one here. Alright, so if we push these off the edge 5 over, well, they go back to the beginning, and rotating it right 5 makes it begin with 6, 8, 90. Okay, so that looks like question 16 is now complete. So let's move on and do question 17. Let's have a read. Alright, so using the functions, integer digits, reverse, from digits, give the binary representation of 221. Then reverse sort the list and produce the base 10 number from the resulting binary number. Okay, so 221 is 1 plus 2 times 10 plus 2 times 10 squared. right? But if I just say n equals 221 and I write integer digits n comma 2, so this says give me the list or array of coefficients in the binary representation of 221. All right, and remember we read these digits with the constant term on the right. Okay, just like it is here. This is the constant term if we're thinking of this, you know, like a polynomial where x equals 10. So this in our sum, remember, I'll just write it out. This is 1 plus 2 by x to the power of 1 plus 2 by x squared, right, where x is equal to 10 in this case. All right, so this should give us 221. All right, so that's what's happening here when I do integer digits, n comma 2, but it's doing it in base 10. Okay, so there we have 221 as the output of this right here, and integer digits, n2 is this array. Okay, so let's just double check that we can reconstruct this. Now I'll call this S, okay, S. All right, now this term, this entry on the right-hand side is the constant term in the expansion. All right, so let's just see if we can reconstruct this with indexing just to double check. All right, so remember indexing, double square brackets, and I'll put a J there. So this is the jth element of the array S. And I want to, well, first of all, let's reverse it, okay? So reverse S, and I'll call this T. Right now I want to take the jth element of T. Okay, so now I want to sum, j goes from 1 to the length of t, and the square bracket for the sum function. All right, but I'm missing something here. I want to multiply by 2 to the power of, now if I start with j equals 1, the constant term will be j minus 1, right? Well, it will have that exponent j minus 1. All right, so let's see what we get now. 221. So that is the output of this, 221. Okay, so this is just like this, but here the x is 2. Okay, so, well, that was somewhat of a digression, I suppose, because I've forgotten what I was doing. So let's have a look. Give the binary representation of 221, reverse sort the list, and then produce the base 10 number from the resulting binary number. Now, what do I really mean by that? Produce the base 10 number from the binary number. Ah, I see. Okay, so I'll comment this out. All right, so I want to work with this, so I've just reversed this, and now I want to produce the base 10 number from the binary number. Okay, so basically I want to do it the other way around, right? So I reverse it, and then I take these coefficients and I turn it back into a binary number. So really what I'm doing here is I'm reading from left to right. So I can go back and call this S. All right, see what we get. It'll be a different number. Well, I need to unsemicolon that. Okay, 187. So that's just basically reading the number backwards and summing it up. Summing up the powers of 2 and giving back the base 10 number. All right, but I think I was meant to do this with some other built-in function. Ah, yes, I intended to do that with from digits. This one from digits. Okay, so let's see what we get. From digits. So in other words, there's a built-in function to do what I just did in a slightly longer way. From digits t, and we'll say 10. I think this is what I want here. What did we get? We just got back the binary number. Okay, so I maybe need a 2 there. Yep, okay, so from digits, and basically what that's doing is it's reading it as a binary number and it'll turn it back into a base 10 number. Okay, so there's a built-in function to do all of this. Okay, so that's that question done. Let's have a look at the next question in this tutorial sheet. Now, it is question 18. Alright, so this one is about using the built-in function power mod. Right, so if you're doing this yourself, I'll reiterate that you would use a technique called repeated squaring. Alright, and I assume that this is part of the built-in function. This is what's going on in the background. Repeated squaring, so you might look that up. Okay, so what do we got? N equals 5519. Okay, so what we want to do is calculate 2 to the power of n, and I'll just show you how big that is. Yep, it's pretty big, isn't it? Goes on and on and on, on and on and on. So if this were bigger, well, you might overflow the memory of the computer and not end up calculating what you wanted. So repeated squaring is a way to, well, I'll just pause there. I'll pause there and say that if you were to calculate this modulo, all right, so let's just say mod 2 to the n when divided by n. All right, so this is the remainder of 2 to the power of n when you divide it by n. Okay, let's see what we get. We get 2, right? But this calculation, what it's doing is it's computing that huge number you saw a moment ago, and then it's taking the remainder when you divide it by n. Okay, so there's an easier way to do that without overflowing the memory, and again, it's called repeated squaring, but there's a built-in function in Mathematica that does this somewhat better, and it's called power mode. All right, so copy this, Control C, Control V, power mod. All right, now I think I want the base first, 2 comma, and I believe it's to the power of n there, and then mod n. Hopefully it's right, otherwise I'll have to look in the help file to double check this. Okay, so we get 2, so I think that's the right syntax for doing it. It didn't complain, so it should be right. Now it's a lot faster. If you want to check how long this took, well, there's another function, timing. All right, timing. This will be such a small time that it won't show up as anything but 0 probably, but we'll have a look. Timing. All right, so the first one took, well, I've got to click here and press enter, right? So then I'll get an actual longer version of the number usually, all right? So, well, they're both so small that it doesn't matter, but if this number n here were larger, you would definitely notice a difference in the timing of these two. All right, I won't do that, just so you know. That's one thing you can use to check how long things take. Okay, so I'll get rid of timing now and proceed to talk about what this problem is doing. Okay, so there's a probabilistic primality test, Miller-Rabin, and tests like this. So basically, it's relying on Fermat's little theorem that says something like, if a to the power of p is, a to the power of p minus 1 is congruent to 1 mod p, and p doesn't divide into a with a zero remainder, then how's it go? I'll just look it up again. Okay, so I'm on Wikipedia. Fermat's little theorem. All right, here we go. If a is not divisible by p, I think I need to maybe make this bigger. Well, my resolution is not good enough, so I'll read it. Okay, so Fermat's little theorem states that if p is a prime number, then for any integer a, the number a to the power of p minus a is an integer multiple of p. Alright, so in terms of modular arithmetic, a to the power of p is congruent to a mod p. So right, the condition is that if p is prime, then you get this congruence. Right, but if you find that the congruence holds, then you don't necessarily have deduced that p is prime. However, if you get enough evidence, well, then you have a lot of evidence that p is probably prime. Okay, so it's really a test of compositeness of the number p. Okay, so if p is prime, I'll write this in comment. If p is prime and p not divides a, comma, then a to the power of p is congruent, okay, congruent to a modulo p. Alright, so that's the result. Okay, now let's proceed to do this. Alright, so what we've got here is that 5,519 to the power of 5,000, no, sorry, 2 to the power of 5,519 is congruent to 2 modulo 5,519. Okay, so what does that say? It says that, well, p could be prime, right? It's not a proof that p is prime, but it could be prime. So if you change the base to 3, 5, other numbers, and get a whole bunch of evidence, where in each case a to the power of p is congruent to a mod p, well, then you might suspect that the number p is prime. Okay, so it's a way to test computationally that p is probably prime, but it's not a proof. And now the built-in function prime q is, I understand it is doing just that in the background, right? It's not using any primality proving mechanism, it is just doing a probabilistic test. Alright, so let's see what we get. We get true down there. So what it's doing is it's going through a number of bases and doing this. Okay, but doing so efficiently with repeated squaring technique. Okay, so now what if I wanted to do a whole bunch of these? Alright, so I would change this to an A, for example, and I would want to be able to change the value of A. Alright, now I'm taking a to the power of n in this case, but if I change this to n minus 1, All right, so let's just put in 3, all right, to the power of n minus 1 mod n. Now this should be 1. All right, so that's the same thing. It's equivalent to testing whether 3 to the power of n is congruent to 3 mod n. Okay, so this gives us the number 1 when the conclusion of this test holds true. All right, so now I'll take this back to A, get rid of this, and now I just want to tabulate over a number of possible A values. All right, I'll keep it small. All right, so table A goes from 1 to 10. All right, so let's see what we get. We get it looks like 10 ones. All right, so we have 10 pieces of evidence that suggest that 5,519 is prime. All right, so if I take this to 100, I will hopefully get 100 pieces of evidence. All right, yes, there they are. And if I don't want to have to look at each one of those individually, I can just write union in front of this bracket, and hopefully I just get the single number 1 to say that in every case 1 was the only distinct entry in there. Okay, so let's have a look. 1, that's correct. All right, so that's that problem. Well, is it done? Check the slow way. Well, we did that too. Okay, so let's just see how far we can go with this. Now, because I'm tabulating, right? So this is constructing a list and putting it in memory. So you really don't want to use table. If you're doing this in a more sophisticated way, you want to use something like a for loop or do, or something like while. All of those are in the help file. Okay, so in general, you don't want to use table, but in a future tutorial, I will show you how to use some of those functions, as in for, do, while, etc. Okay, but for now, let's see how far we can go with this. 1,000, yep, good. 10,000. Now at 10,000, we suddenly get a 0. Why? Well, because 5,519 itself is one of the possible A's. Okay, so when A is equal to 5,519, that's congruent to 0 mod n, and that's where we get a 0. Okay, so you can go up to n minus 1 in this case, and all good. This suggests that you have 5,518 pieces of evidence that the number n is prime. All right, so thank you for listening. Hope you enjoyed this. If you did, please click like and subscribe. Thank you. Bye for now.